Normal distributions, part 1. We'll go ahead and get right into our student notes. Let's go ahead and look at a preview to normal distributions. Random variables can be either discrete or continuous. Continuous variables, such as height of adults and body temperature of rats, can assume all values between any two given values of the variables. Although no variable fits a normal distribution perfectly, the normal distribution can be used to describe many variables since the deviation from a normal distribution are small. Here's the definition of the normal distribution. If a random variable has a probability distribution whose graph is continuous, bell-shaped, and symmetric, it is called the normal distribution. The graph is called a normal distribution curve and looks something like this. Here's the mathematical equation for a normal distribution. Now it looks quite complicated, but thankfully we actually do not use it that often. But occasionally when we do, it is quite useful. Keep it in mind that E is 2.718 rounded, and pi obviously is approximated at 3.14. Also, mu is the population mean as usual, and sigma will be the population standard deviation. The shape and position of the normal distribution curve depend on the parameter population mean and the parameter population standard deviation. The shape of a normal graph will essentially be bell-shaped. And when the population means are the same, but the population standard deviations are different, the curve with the larger population standard deviation is more spread out. Here is a picture where we have the same means, but different standard deviations. Notice that the graph with the higher standard deviation is more spread out. Also, when the population standard deviations are the same, but the means are different, the curves have the same shape, but are centered at different points along the x-axis, as you can see here. Here's a summary of the properties of the theoretical normal distribution. Again, the normal distribution curve is bell-shaped. The mean, median, and mode are located at the center of the distribution. The normal distribution curve has exactly one mode. The normal distribution curve is symmetric about the mean. The normal distribution curve is continuous, having no gaps or holes, for all values of the independent variable. The curve approaches but does not meet the x-axis, getting increasingly close while never touching the x-axis. Also, the total area under a normal distribution curve is equal to 1. Moreover, the area under the part of the normal distribution curve that lies within one standard deviation of the mean is approximately 68% of the data. Within two standard deviations of the mean is approximately 95% of the data. And within 3 standard deviations of the mean is approximately 99.7% of the data. This is known as the empirical rule. In the next slide, we'll illustrate what this looks like. Once again, here's the mean. And if we go one standard deviation to the right and to the left, This will cover about 68% of the entire data. If we go to the right and to the left, 2 standard deviations from the mean, that includes 95% of the total data. And finally, if we go to the right and to the left, 3 standard deviations, that will include almost all of the data, 99.7% of the data. The normal distribution is symmetric about the mean. That is, the data is evenly distributed about the mean. When the majority of the data values fall either to the left or the right of the mean, the distribution is what's known as skewed. When the majority of the data is to the right of the mean, the distribution is negatively skewed or left skewed. The mean is less than or to the left of the median. However, when the majority of the data is to the left of the mean, the distribution is positively skewed or right skewed. The mean is greater than or to the right of the median. So to identify symmetric or skewed distributions, we notice that the tail of the curve indicates the direction of the skewness. A tail to the right is positive, and a tail to the left is negative.